BackportBench, a multilingual benchmark for automated patch backporting. In modern software development, projects evolve rapidly, adding new features, fixing bugs, and patching security vulnerabilities. But while developers fix issues in the latest version, older versions often remain unpatched. Users who depend on these older versions are left exposed to known vulnerabilities. The solution: patch backporting, adapting a fix from a newer version and applying it to an older one. It allows users to stay secure without upgrading, which can be costly or even impossible due to breaking changes. But here's the catch: manual backporting is slow, error-prone, and rarely done at scale. And until now, there's been no standardized way to test or compare automated techniques for this task. Today, we introduce BackportBench, the first comprehensive multilingual benchmark for automated patch backporting. Built from real-world vulnerabilities in PyPI, Maven, and NPM, BackportBench contains 202 real-world backporting tasks, each with executable Docker environments and full test suites to validate results. This isn't just another dataset. It's a practical, execution-based benchmark that reflects the true complexity of real-world software maintenance. Unlike previous work that focused only on small code hunks or function-level changes, BackportBench operates at the repository level, requiring systems to understand code across multiple files, structural differences, and semantic evolution between versions. So why does this matter? Because current automated approaches have serious blind spots. Many early methods relied on rigid handcrafted rules, like fixmorph, which uses syntactic transformation rules in the Linux kernel. Others, like tsbport, use dependency graphs to locate patches. These work well in narrow contexts but fail to generalize. More recently, large language models, LLMs, have shown promise. Approaches like PyPI and MistIke use fine-tuned LLMs to port patches by stripping context or extracting semantic signatures. But they're still limited, focused on isolated functions, not cross-file changes. And evaluation: it's broken. Most studies rely on syntactic or semantic equivalence to the human-written ground truth. But that's too strict. A patch that doesn't match exactly can still be correct, especially when it requires logical or structural changes. Worse, many rely on similarity metrics like CodeBLEU, which are unstable and don't capture real effectiveness. BackportBench fixes this. Each task is validated through execution. We run the test suite before and after applying the patch. A backport is only considered successful if it fixes failing tests and preserves existing functionality, a much more realistic standard. We built BackportBench through a rigorous pipeline. Starting with the OSV vulnerability database, our primary source, we mined over 37,000 records, filtering for vulnerabilities with multiple commits across different versions. After deduplication and filtering for valid, testable patches, we ended up with 619 candidate pairs. Then came the hard part: manual validation. 2 researchers independently reviewed each pair, checking commit messages, code changes, and version tags to confirm genuine backporting relationships. Only 202 passed. These 202 instances are not just data, they're insights. We categorized them by file level and content level changes. The results are revealing. 91.9% of backports modify the same files as the original patch. But 21.8% require logical or structural changes, like adding new functions, restructuring control flow, or adapting to missing APIs. And 47% of these backports address vulnerabilities rated critical or high severity, meaning they're not trivial fixes. This tells us something important. High-quality backporting is rare, and when it happens, it's often for serious issues. But developers are reluctant to do it, especially when it requires major changes. Now the big question: how well do automated tools perform? We evaluated 3 leading approaches: SWE-agent, a state-of-the-art agentic framework; agentless, a procedural method; and Oracle Retrieval, a baseline that gives the model perfect file localization. We used 3 top-tier LLMs: GPT-5, Claude Sonnet 4, and QN3 Coder. The results: agentic methods win, hands down. SWE-agent with Claude Sonnet 4 achieved a 70.8% resolution rate across all languages. That's significantly higher than agentless, 46.5%, and Oracle Retrieval, 68.8%. But here's where it gets interesting. Performance varies wildly by language. On Python, SWE-agent hit 91.1% success. On Java and JavaScript, down to 46.3% and 43.5%. This isn't just a minor drop, it's a fundamental gap in generalization. Why? Because LLMs struggle with Java's verbosity, JavaScript's dynamic nature, and the complexity of cross-file reasoning. Even SWE-agent, with its planning and reflection, can't fully overcome this. More telling, the hardest cases are the ones most ignored. When a backport only needs a location change, moving a patch to a different file, SWE-agent performs better than on no-change cases. That's counterintuitive but makes sense. It's easier to move a patch than to rewrite it. But when logic or structure changes are needed, like implementing a missing function or reorganizing a control flow, even the best models struggle. MistIke, the previous state-of-the-art patch porting tool, resolved only 40.3% of complex Java cases. SWE-agent, in contrast, managed 46.3%, a 15% improvement. And here's a red flag: Mistake often breaks existing functionality. Its patches pass the fixed test, but fail on tests that verify original behavior. This is a critical flaw. Most prior work never caught it because they only checked equivalence. BackportBench exposes this. It forces models to not just fix the bug, but preserve the system. So what's next? For researchers, this benchmark is a wake-up call. We need better tools that understand cross-file context, structural evolution, and semantic drift between versions. We need models that can plan, reflect, and retry, like real developers. For practitioners, always test backported patches. Just because the code looks similar doesn't mean it works. And don't assume a patch is safe just because it applies cleanly. BackportBench isn't just a testbed, it's a mirror. It shows us where we are and where we must go. We've open-sourced the entire benchmark at github.com/backportbench/backportbench, complete with Docker images, test scripts, and documentation. This is the foundation for the next generation of automated patching. The era of equivalence-based evaluation is over. The future is execution-based, multilingual, and real-world. Because in software security, patching isn't just about code, it's about trust. And trust only comes when the fix actually works.